This lesson is about de Moivre's theorem. De Moivre's theorem is an awesome shortcut for raising a complex number to a power, and we are going to get there in this video. But in order to understand de Moivre's theorem's origins, I have to share some historical mathematical discoveries with you that are going to require a lot of very ugly algebra. And when you see this really messy algebra and arithmetic, it's important to remind yourself that the algebra you're watching is less important than the discoveries that the algebra led to. So don't let yourself get overwhelmed by the messiness of the computations. We're going to start with multiplying complex numbers in polar form. I'll share this discovery with you as a stepping stone to get to de Moivre's theorem. Here's a multiplication problem, complex number times a complex number. And you'll notice that these are not in polar form, that they're in rectangular form. Putting that thought aside, let's watch what would happen if we were to multiply these two complex numbers together. You'd essentially have to use FOIL or something like it. And just to give you a sense of where all these sixes came from, I'll show you this one part. If we were to multiply those together, the algebra would ultimately lead to a result of -6. And if I were to continue to simplify, the 6i terms in the middle would cancel out, remembering that I squared is -1 ultimately leads me to a result of -12. Again, don't let the algebra overwhelm you. It's not the main point of what we're doing here. What we're doing is looking at some results from centuries ago that are going to lead us to a better understanding of ultimately what de Moivre's theorem is. So the result is -12. But what if we were to look at these numbers not as rectangular complex numbers, but rather as polar complex numbers? So here's what was discovered in the mid-17th century. If we were to take this complex number by the red arrow, show its rectangular coordinates, we would discover that we had a 45, 45, 90 triangle because of the equal legs. And therefore, the hypotenuse, or modulus, would be radical 2 times the leg, which in this case is 2. And so what this diagram shows is that we're 2 spaces away from the origin at a 45-degree angle, and hence the polar coordinates here. Likewise, if we were to convert this complex number into polar coordinates, we would discover that we had a 45, 45, 90 triangle again for the same reason, and therefore this angle in blue here would be 135. The hypotenuse would be radical 2 times the leg, which by the way works out to 6, showing that we are 6 units from the origin at 135 degrees. What about the result -12? Well, if we thought of -12 in polar coordinates, we could express it as -12 plus 0i, reminding us that we were 12 spaces away from the origin to the left at an angle of 180. But what I've done here is I've taken a multiplication problem and its answer, and I've converted everything in that line to polar form. Why would we do that? Well, here's the discovery that was made, and maybe you'll see it too. Watch the boxes as they appear. The discovery was made that if you are multiplying in polar form, that you just multiply the moduli together. In other words, 2 times 6 is 12. And another discovery was made here. You may see it before I mention it. In this case, they discovered that, strangely, when you're multiplying complex numbers in polar form, the angles end up adding together for whatever reason. Strange as that may seem, it's not an addition problem, but that discovery was made. So let's take this one problem and generalize. What can we generally say about multiplying complex numbers in polar form? Well, Well, what this example shows is if you have a complex number multiplied by another complex number, you could express your result this way, which is simply a formula to show us the idea that we discovered above, namely, you multiply the moduli and you add the arguments or angles. This is the first result necessary in an understanding of de Moivre's theorem. Let's now look at a division problem in polar form. Here's a division problem, complex numbers, but as you can see, it's not in polar form. These are rectangular complex numbers. But let's examine the result of this problem and see what kinds of discoveries they might have made about division. As you'll recall, if we're dividing numbers in rectangular form, we can multiply by 1 by using the conjugate of the original denominator. And it gets pretty messy here, but when you do FOIL or some similar process to the tops and bottoms, a lot of ugly algebra happens. Again, it's not really the focus here, but I simplified all this ugly algebra using the fact that I squared is -1, and it ultimately led me to this problem having a solution of 4i. Fair enough. Now if you got lost in the arithmetic there, put that aside. There's a bigger picture that I don't want us to miss here. Here's the solution to this rectangular form division problem. So again, in the middle to late 17th century, they started to wonder, what would this problem look like if the problem and the answer were expressed in polar form rather than rectangular as they are now? So taking the first one, converting to polar form, leads you to the following. If you're a little rusty on your complex number conversion, now would be a good time to pause the video and examine the diagram. Otherwise, we'll move on from that. Same concept for the denominator. Expressing that in polar form ultimately leads us to the complex number 2, 30 degrees. Again, if you're not super comfortable with that, this would be a good time to pause the video and think about it, or even go back to the video called Complex Numbers, Polar and Rectangular Form, which gives a much more detailed outline of where all these numbers came from. And the result, which we found to be 4i, could be thought of as the point 0 plus 4i. And what would that look like in rectangular, in polar form? Well, it would correspond to the point 0, 4. In other words, it would be 4 spaces from the origin at an angle of 90 degrees, hence 4, 90 degrees. So what we've done here is express a complex number problem that was in rectangular form in polar form. And the purpose is to show you a cool trick that was noticed by early mathematicians. And you may see it here already. They noticed that when you divide the moduli, 8 divided by 2, you get the modulus of the solution. And they further noticed that if you subtract the angles in the division problem, you get the angle in the answer, essentially. Could we state this more generally? Sure, we could if we look at it this way. Imagine we have some complex number in polar form and we're dividing it by some other. Well, what this example shows is that you can use this formula as a means to get the solution. But these symbols are simply reminders to tell us that we're dividing the moduli and subtracting the arguments. So we're now one step closer to building the idea of what de Moivre's theorem is. De Moivre's theorem is ultimately about raising a complex number to a power. Before we talk about it in general, consider this problem. If we wanted to raise something to the third power, of course we would take that thing and multiply it by itself and multiply by itself again. No mystery there. But using the result that we saw above about multiplying complex numbers, we could basically just do 4 times 4 is 16 and add the 60s to get 120. But then I could further multiply by using the same trick of 16 times 4 and 120 plus 60, ultimately leading me to this. But let's think about where the 64 and the 180 came from. 64 came from 4 times 4 times 4, and 180 came from 60 plus 60 plus 60, or 60 times 3. In other words, if you compare these two side by side as I've done here, you can start to see what de Moivre ultimately realized. Let's talk about this in more general terms. De Moivre realized that if you're raising a complex number to a power, let's just generically call it this, that you can raise the modulus to that power and multiply the angle by that power. And that was de Moivre's ultimate discovery. And finally, we have achieved de Moivre's theorem. And in the last part of this video, I want to show you a very awesome shortcut that you can use de Moivre's theorem on when solving your own math problems. Here's an application. Suppose we were going to raise this ugly complex number to the third power. Now notice at the current moment it's not in polar form, so de Moivre's theorem does not apply. If we wanted to work this out manually, we would have to multiply 3 factors of this number together, and it would get very, very messy here. If you're interested in following every detail of the arithmetic, now is a good time to pause the video and analyze the numbers of what ultimately led us to negative 64. But it's very unlikely that you'll ever have to do this kind of arithmetic, especially given de Moivre's shortcut that we're about to see. So let's put that arithmetic aside and examine a better way. What if we were to take the number that we were raising to the third power, the one you see here in the brown box, what if we were to take that number and express it in polar form? If we did, we could then raise it to the third power using de Moivre's theorem. If you got lost in that, watch and you'll see. This picture represents that complex number. Notice I'm not talking about the third power here, just the number inside the parentheses. And because these legs are in a radical 3:1 ratio, we must have a 60-degree triangle, and as usual the hypotenuse would be double the shortest leg. If this is an uncomfortable math topic for you, I recommend going back and watching the special triangles video. Otherwise, we'll move on. At this point, we know that we are 4 spaces from the origin at a 60-degree angle. In other words, we've expressed our original problem in polar form. Now, why would we bother? Well, because when it's expressed in polar form, we can now apply de Moivre's theorem. De Moivre's theorem says I can raise this to the third power by just doing 4 to the third power and 3 times 60, which, if you simplify, leads you to this. But didn't we just work this out a minute or two ago and find out that the answer is negative 64? Well, that is in fact what 64, 180 is. Let's remind ourselves that 64, 180 represents a point that's 64 spaces away from the origin at an angle of 180 as shown in the diagram here. But isn't that the same as the point negative 64, 0, which is essentially the number negative 64 on the x-axis? And what this example shows is that de Moivre's theorem can be used to dramatically cut down on your work and the amount of messy algebra that you'll need. Now you might be saying to yourself right now, I would rather do all that messy algebra than deal with polar trigonometric numbers and angles, and if you have a kind of a weakness in trigonometry, then that probably is a strong feeling. And there's nothing wrong with working these out manually, but might I suggest that if instead of, say, raising this problem to the third power, we were raising it to the seventh, there's absolutely no way you could get a correct answer with the amount of arithmetic that would entail. So you can definitely see the positive application of de Moivre's theorem, especially as the exponent grows. I hope this lesson was helpful. That's the conclusion.